So this is the volume in which the gas molecules are enclosed. So as they are in a state of constant motion, in 9 seconds, we get 9 hits. That means 1 hit per second. Now, if the volume of the container is reduced to half, so you observe that in 9 seconds again, there are 18 hits. So as the volume of the container is reduced to half, the number of hits per second increases or doubles. So initially we had a volume, so we got 1 hit per second. Now when we reduced the volume of the container to half, we got 18 hits in 9 seconds. That means we got 2 hits per second. So on reducing the volume of the container to half, the number of hits per second doubles. So we saw that in 9 seconds, we got 9 hits. So there is 1 hit per second. Now, when the volume of this vessel was reduced to half, in the same time, that is in 9 seconds, there were 18 hits. That is, there were 18 hits in 9 seconds, so there were 2 hits per second. So on reducing the volume to half, the number of hits per second doubled. So what do we observe? We observe that as the volume decreases, the pressure increases. Why is this so? This is because as the volume decreases, there is lesser space for the same number of molecules to travel. So they hit the walls of the container more. As the number of hits per unit time increases, the pressure increases. So this law was given by Boyle, which is known as the Boyle's law. He said that the volume of a gas is inversely proportional to its pressure, provided the temperature remains constant. So we see that we get volume is equal to constant by P. So to remove the proportionality sign, we introduce a constant. So we get that pressure into volume is constant. So if we have a particular temperature and a particular pressure, there is a fixed volume of a gas. So for a particular pressure and a particular temperature, there is a fixed volume of a gas. So, how do we read this equation now? So far, we have seen that whenever we are given any chemical equation, we read it as, say in this case, there is no coefficient. So this means there is one molecule. So we read it as one molecule of oxygen reacts with 2 molecules of hydrogen to give us 2 molecules of water. But years back, it was not easy to count the number of molecules. The scientists did not have sophisticated instruments to measure the number of molecules of the substances. So what they did, they measured the substances in terms of their volumes. The first scientist to do this was Gay-Lussac. He observed that for the same equation, when oxygen reacts with hydrogen, one volume of oxygen reacts with 2 volumes of hydrogen to give 2 volumes of water. This means that, say, 1 liter of oxygen reacts with 2 liters of hydrogen to give 2 liters of water, or 2 liters of oxygen reacts with the double amount, that is 4 liters of hydrogen to give 4 liters of water. So what is observed here is that the substances or the gases in this case, they react in volumes. And if you observe, in this case, 1 volume of oxygen reacts with 2 volumes of hydrogen. So what is the ratio of oxygen is to hydrogen? We get 1:2. So if there is 1 liter reacting with 2 liters, again the ratio is 1:2. Or if there are 2 liters of oxygen reacting with 4 liters of hydrogen, again we get 1:2. So this is the ratio in which oxygen combines with hydrogen. Now if we look at the ratio of, say, oxygen is to water, in this case water is formed in the form of steam. So this is also in the gaseous state. So if we take oxygen is to steam or oxygen is to water vapor, we get 1 volume of oxygen gives 2 volumes of steam. So again, the ratio of oxygen is to steam remains 1:2. Gay-Lussac observed some other gases. So for this reaction, nitrogen reacts with hydrogen to form ammonia gas. So in this case, he observed that 1 volume of nitrogen reacts with 3 volumes of hydrogen to give 2 volumes of ammonia. That means that nitrogen reacts with hydrogen in 1:3 ratio. And nitrogen forms ammonia in the ratio 1:2. That is, 1 volume of nitrogen is required to form 2 volumes of ammonia. If we look in terms of hydrogen and ammonia, so we see that 3 volumes of hydrogen give 2 volumes of ammonia. So this is the ratio of hydrogen is to ammonia. Let's take another example. In this case, carbon monoxide reacts with oxygen to form carbon dioxide gas. Again, 2 volumes of carbon monoxide react with 1 volume of oxygen to give 2 volumes of carbon dioxide. So if you observe the ratio of carbon monoxide is to oxygen, we get 2:1. And if we observe the ratio of carbon monoxide that gives carbon dioxide, we get 1:1. So based on all these observations, Gay-Lussac gave his law, which is known as Gay-Lussac's law of combining volumes. Since he had observed that gases react in volumes, so he gave his law of combining volumes, which states that whenever gases react, they do so in volumes. And this bears a simple whole number ratio, as we've seen before. So whenever they react in volumes, they bear a simple whole number ratio to each other and to the volume of the product which is formed. But one important condition remains, that is, all the volumes are measured at the same temperature and pressure. Provided all the measurements for a particular equation are taking place at the same temperature and pressure, the Gay-Lussac's law of combining volumes holds. That is, whenever gases react, they do so in volumes and it bears a simple whole number ratio to each other and to the product which is formed. The volumes of solids and liquids are taken to be 0. This is because if there is some amount of heat given, the change in the volume of gases is remarkable. Even a little heat supplied to gases changes its volume to a large extent. But a little heat does not change the volume of solids or liquids. So the change in the volume of solids and liquids is quite negligible. That is why the volumes of solids and liquids is considered to be 0. And we always take into account the volumes of the gases. There's an industry, Fisher Pharma industry. The industry manufactures a medicinal drug comprising of nitric oxide, which is used as an energy booster. NO, that is nitric oxide, is produced by a reaction involving oxidation of ammonia. If 100 liters of ammonia is used, what is the amount of nitrogen oxide produced? So this reaction is used to make or produce nitrogen oxide. So by Gay-Lussac's law of combining volumes, we know that whenever gases react, they react in volumes. So we are given 100 liters of ammonia is used. If we take the ratio of ammonia which is used to form nitric oxide, we see that 4 volumes of ammonia is used to form 4 volumes of nitric oxide. That is 1:1 ratio of ammonia and nitric oxide is present. 4 volumes of ammonia produces 4 volumes of nitric oxide. So 100 liters of ammonia produces 100 liters of nitric oxide. So whenever gases react, they react in volumes that bears a simple whole number ratio. So if you see the ratio of ammonia is to oxygen, it's 4:5, and ammonia is to nitric oxide, it's 1:1. Keep in mind, the water formed in this case, this subscript L shows that it is in the liquid state, so the volume of water is 0. So in this case, we get 4 volumes of ammonia giving 4 volumes of nitric oxide. So 100 liters of ammonia used in the reaction produces 100 liters of nitric oxide. Now, you all must have used a balloon, you must have inflated a balloon. What happens? As you pass air in the balloon, a deflated balloon increases in volume. So let's see what happens. Now, as you pass more and more air into the balloon, the volume starts increasing. This is because when you're passing more air, you're passing more number of molecules in the balloon. So, as more air is passed, the number of molecules of air which are now passed in the balloon increases. As the number of molecules of air increases, the balloon starts expanding in volume. And whenever you deflate it, that is, you allow the air to be expelled out, so the number of air molecules is decreasing, so the volume of balloon also starts to decrease. So in this case, that is, in your day-to-day life, you have observed a relationship between the number of molecules and the volume. Something like this was observed by a scientist in 1811. So in 1811, there was a scientist who observed that if there are two gases at the same temperature and pressure, equal volumes of the gases contain equal number of molecules. This scientist was Lorenzo Romano Amedeo Carlo Avogadro. So Avogadro observed that for any two gases, if there is same temperature and same pressure, so equal volumes. So we know that at the same temperature and same pressure, a gas occupies a fixed volume. So for the same temperature and same pressure, equal volumes of any two gases contains the equal number of molecules. So based on this observation, Avogadro gave his law, which is known as Avogadro's law. It states that equal volumes of all the gases under similar conditions of temperature and pressure, they contain the same number of molecules. So this holds for all gases. All the gases, if we have equal volumes of all the gases at the same temperature and pressure, they all contain the same number of molecules. So, if we have the same temperature and pressure, we are given two gases, oxygen and hydrogen. They contain the same number of molecules. That is, oxygen contains 50 molecules and there are 50 molecules of hydrogen. So when there are same number of molecules of two gases, this means that they occupy the same volume. So Avogadro states that equal volumes of all gases under the same temperature and pressure contains equal number of molecules, and vice versa. If we have two gases containing the same number of molecules, this means that the two gases occupy the same volume. Avogadro's when presented his work initially, his work was rejected. Nobody was ready to accept that gases react in molecules. But later experiments were performed and it was found out that yes, Avogadro was right. But unfortunately, that was after Avogadro was dead. So again, we have the same industry, that is Fisher Pharma Limited, which produces a drug that uses nitric oxide. In this case, we have the industry is producing the drug using nitric oxide. Under the same conditions of temperature and pressure, which of the following species contains the maximum number of molecules? Now, first of all, we observe that water is in the liquid state. We know that the volume of solids and liquids is considered to be 0. So the volume of water in this case is considered to be 0. Now if we see, we observe that 4 volumes of ammonia reacts with 5 volumes of oxygen to give 4 volumes of nitric oxide. By Gay-Lussac's law, we know that gases react in volumes. So by this we have ammonia reacts with oxygen in 4:5 ratio, and ammonia produces nitric oxide in 4:4, that is 1:1 ratio. Avogadro states that under the same conditions of temperature and pressure, equal volumes of all gases contain the same number of molecules. So if the volumes of the gases is same, they have the same number of molecules, this means that the gas which has the greatest volume, or the gas which occupies the greatest volume, has the greatest number of molecules. In this case, we observe 4 volumes of ammonia, 5 volume of oxygen, and 4 volume of nitric oxide. This means that ammonia and nitric oxide contain the same number of molecules. Since the volume of oxygen is the greatest, so oxygen has the greatest number of molecules. So by Avogadro's law, under the same conditions of temperature and pressure, the gas which occupies the maximum volume contains the maximum or the greatest number of molecules.